we can put this again. Yeah. Yeah, go ahead. You can ask your question.
Sir, like I tried solving with the homework questions you gave in between.
Yeah, okay. Which one? Let's see. What's it's
Yeah,
8:30, right? Okay, so we still have around 20 minutes. One second. Let me share content, share screen. Yeah, tell me which problem. So lecture 26. Which lecture?
sir, in the HSW theorem proof.
Okay, so that is lecture number.
Lecture number 22. Sir. 22.
Okay, here it is. Yeah.
Yeah. In the first question, you asked us to take expectation and then prove that something is very small in the first question.
Correct. This one, right?
Yeah.
Yeah. So yeah. So yes. Okay, great.
Like I don't know if it's correct. So like I
If you
use
want, you tell me. I'll write. Hold on.
yeah. Okay.
Sorry, did I miss anything? I just
No. I'll tell you what he's
okay.
asking. Okay. So what Srinidhi is asking is he's trying to solve some of the questions I asked in the lecture, and he is pointing to lecture 22 HSW theorem proof. And I gave the
Okay.
proof of this theorem. So, I designed the code scheme, and then I came up with the POVM, and then I started to analyze the error probability. So if you recall, yeah, I designed the code here, and then okay, so let me use this. Actually, I forgot using this. Yeah. So I designed the code here. This is very good. This pointer is very good. I designed the code here. I designed the POVM, and then I started to analyze the POVM. And initially I put this indicator function and this indicator function, and then I separated the two terms, and then I asked one of the terms, you show it by expectation, you can show that that term is small. This is what I said. And
Okay.
is wanting, I think he is wanting to check if his proof is correct. So yeah, go ahead, Srinidhi. So wait, let me copy that. So you want that very thing, right? This very thing, right?
Yeah.
Actually, this notes and this lecture videos are actually good because you can actually explain quite well. Yeah, okay. So you want to show this, right?
Yeah. So like the expectation is over the code word again here, right?
Correct. So yeah, you're looking at something like this. Expectation.
Yeah.
So I'll write this down and then you tell me.
Yeah.
This is what you're looking at.
Yeah. So like
Expectation is
these
guys.
Yeah. So like I used Hayashi Nagaoka also. Should we use or like
No, you don't need Ayash Nagaoka, but let's see. So I think this is rho sigma, and this is rho xn of m, I think, right?
yeah.
Fine. There may be an eta 1 here and an eta 2, something like that. I don't know what, it doesn't matter really. Did I do the etas or did I do delta? What did I do? S was S. Yeah, S was here. I just wrote pi m pi. Yeah. So yeah, so so if you want, the definition is here. Okay. So yeah, okay. Tell me what you do, Srinidhi.
Yeah, like now it's just the probability of x and m multiplied by this term. This
Correct.
whole
So it's something like this, right? So
the
it's
summation over x and then the probability this term into p.
yeah. So first step, I can do this, right?
Yeah,
I can do this, right?
yeah,
Yeah. Then what?
yeah. Then I'll multiply. So this will be summation over
Okay.
xn, p of xn and the whole term.
So let's do one thing. Let's just take one term.
Yeah.
Do you agree?
Yeah.
Okay, now tell.
So now like as this we have this indicator random variable.
Sorry.
So this yeah. So
You have this, right?
yeah. So this
Yeah.
probability is like very less because it is outside of typical set.
Okay, but still you have to show this. I mean, you have to show
Yeah.
what
Yeah.
do you do?
So like I applied this Hayashi Nagok and split it and then tried.
Okay, you will apply Hayashi Nagoka here.
Yeah.
You will be in trouble, I think. Okay, let's
Then,
do. If
then
if
I
I
will get
if I no hold on, I'll just
huh.
make one comment.
Yeah.
If that was the method, right, then why did I separate and then apply Hayashi Nagoka only one part? Remember?
Yeah. That's why I wanted to ask.
Yeah. So
So,
suppose that was the way to go, then I would not have done the splitting, because what I did the splitting and applied Hayashi Nagoka only on the part where xn belongs to T delta n, correct?
yeah.
When xn
So
doesn't belong
like,
to T delta n, left it to you.
yeah. The other way I tried is like this summation is like equal to summation over xn's which are not in T delta n and this whole term.
Think very simple. Think very
So actually, the trace is there, right?
yeah.
Uh,
Think very simple. If there is any use of Hayashi Nagaoka, I would have done it myself, right?
so you can just upper bound the big inner term by I tensor n.
Hold on. Write down. Tell me, I'll write down.
Yeah, so it is summation pnx xn
Okay.
trace of rho xn and then the indicator.
Why is this true?
Because this s plus t raised to minus half s times s plus t raised to minus half is PSD.
So let's ensure Srinidhi ask you the question. So Tejas is saying this. Do you agree with this?
Yeah, because S and T are PSD.
No, because see, whenever, so the idea is, so so any so if A is greater than B, then
Yeah.
X A X dagger is greater than equal to X B X dagger. Do you agree?
Yeah.
So S is greater than 0. Why is S greater than 0? Because S is pi m pi. right?
Yeah.
So pi m is greater than 0, which means that pi m pi is greater than 0, is greater than pi 0 pi, which is 0, right? I'm
Is
telling
this
you
just pi
all,
m?
no, I'm telling you all the steps. S is pi m pi, right?
Just pi m, I think, in this.
No, no, no. What is this? Huh? Oh, yeah. Oh, I didn't put the pi. Ah, okay, great. Then it's even simpler. Okay, awesome. Thank you. So then you don't have the pi. So S is pi m, which is definitely greater than or equal to 0, right? It's a projector.
Yeah. Yeah.
So if you put S plus T on the left and S plus T on the right with a minus half, it's still greater than or equal to 0. So this you agree?
Yeah.
So now what?
So now, like, xn does not belong to
No,
typical
no, no.
set.
Now what? Now after this what?
Oh, yeah. So I minus this one is like greater than 0.
Huh? What is this?
I, yeah.
This is
mm, less than I.
less than I.
Yeah.
Sure. See, A is greater than B means I minus A is less than I minus B, right?
Yeah.
That's all. See,
Yeah.
this is greater than 0, which means I minus this is lesser than I minus 0.
Yeah.
Okay?
Yeah.
Okay, so let's go step by step. I'll write it once again. So I is pi m, S is pi m, S is greater than or equal to 0. This implies S plus T whole power minus half, S plus T whole power minus half is greater than or equal to 0. Agreed? I
Yeah.
minus S plus T whole power minus half, S plus T whole power minus half is less than or equal to I minus 0. Agreed?
Yeah.
Trace of I minus S plus T whole power minus half, S plus T whole power minus half into rho xn is less than equal to trace of I minus 0 rho xn. Do you agree?
Yeah.
Why?
Like
Why?
rho xn is a positive semi-definite.
Okay. So
And
if A is greater than B, is trace AC greater than equal to trace BC?
like if C is PSD.
Ah, exactly. If C is PSD, C, you gotta be careful. C, you gotta be careful, very careful. If A is greater than, so forget all this. If X is greater than equal to 0, all of you be very careful, okay? If X is greater than equal to 0, Y is greater than equal to 0, you cannot say XY is greater than equal to 0. But you can say trace XY is greater than equal to 0. Okay? What I'm now
Yeah.
using, I'm saying X is, I'm saying X is S, okay, I'm saying X is I'm saying X is S plus T whole power half, S plus T whole power half, minus half. And I'm saying Y is rho xn. So this says that, or I can do, well, I can say X is, I want what do I want? I want. Okay, that's fine. I can say this. I can say this. X is this. So I have trace x, y to be greater than or equal to 0, which means trace rho xn minus trace xy is less than or equal to trace rho xn minus 0. Do you agree?
Yeah.
Comfortable, Srinidhi, if you're not comfortable, let me know. I'll explain.
Okay. This is okay.
This is okay. So that
Yeah.
means I can say that this guy is lesser than trace of I times rho xn, right? So if I go here, what do I get? So now do you agree with this?
Yeah.
Now you know how to proceed?
Yeah. Like, I can take the summation over just the extents which are not in typical set.
No. This I can say is p xn of xn,
Yeah.
p xn of xn times
Yeah.
1 times indicator function of xn not in
Yeah.
typical set, right?
Yeah. Yeah.
This is done, right?
Yeah. Yeah. So that's yeah. So
Minus
this is
n.
very yeah.
Yeah. So that's the idea. That's why it was simple. That's why I left it. You understand now, right?
Yeah. Yeah. I got this.
Okay, good. Next.
Sir, while I was reading the
Yeah.
gentle measurement, so
Yeah.
like we have this root lambda, rho root lambda, right?
Hold on. Gentle measurement. Yeah. Yeah, I think he has this. He has this. Okay. No. He has this. Rho minus root lambda, rho root lambda.
Root lambda. Yeah. So like should it be like square root on both sides always? Like should the operator like
Yeah.
he said
See,
that the
I'll tell
condition
you.
he needs, yeah.
I'll tell you. See, I'll tell you this POVM panda. See, general measurement is MK. General measurement in quantum is MK satisfying MK rho, MK dagger, MK is identity. This is what is the general measurement. And when you do this measurement, you will end up in state MK rho, MK dagger divided by trace MK rho, MK dagger. Okay.
Yeah.
Now, the idea is, see, if you are only looking at the outcome statistics, if you're only interested in outcome statistics, right? So trace MK rho, MK dagger. This is the outcome statistics. This can be written as trace MK dagger, MK rho. Now this is a positive semi-definite operator.
Yeah.
Okay, so what they do, people call this, so let's define a POVM, lambda k, written as MK dagger MK. Okay, so then if I just define a positive operator lambda k that sums to identity, so lambda k, sum of lambda k is identity, then I'm getting the statistics of this measurement MK, correct?
Yeah.
But I'm not getting the post measurement state.
Hmm.
Post measurement state is this. So what they do is they will just associate MK with root lambda k. And so that's why they're saying the post measurement state is root lambda k, root lambda k. They should have a trace at the bottom, but he's interested in a different quantity there.
Yeah.
That's why he is looking at m root lambda k, rho root lambda k. So it is what is happening. So that's why he's looking at this. See, what is happening is the following. Suppose I take, so suppose I have two measurements, mk, let's call it mk, k belonging to k, one measurement. And I have another measurement, let's say sk, k belonging to k, with the relationship that with the relationship that UMK is say SK, or rather, no, I'll write USK is MK, and U is some unitary. Okay, observe the following. So suppose I do SK dagger SK. What do I get? I get so SK is U dagger MK. So SK dagger is MK U dagger. So if I do this, right, MK U dagger U
A
MK.
dagger, U dagger.
So this I'll get as MK dagger.
Yeah.
Yeah, I'm going to get, so I made a mistake there. That's fine. SK dagger is MK dagger U. So MK dagger U, U dagger MK, correct?
Yeah.
Because SK is U dagger MK. And SK dagger is MK dagger U. And hence summation SK dagger SK is identity. Okay.
Yeah.
What is trace SK row SK dagger? This is same as trace. What is SK? SK is U dagger MK. I'm copying from here. Row SK dagger is MK dagger U. Correct?
Yeah.
This is same as trace MK row MK dagger because U outside can be kicked off.
Yeah.
Okay.
Yeah.
So the statistics of both SK and MK are identical. And both SK and MK are operators. Now, if you if you now define lambda K, right? Lambda K as root SK dagger SK, this will give you the same statistics of both SK and MK. But only the post measurement state, there will be some rotation problem. You see?
Yeah. This due to that unitary.
Do you want me to explain again slowly?
Yeah, like I understood, but the
Yeah,
rotation.
okay. So let me explain. See, suppose I take a measurement MK and I define a new set of operators SK as U dagger MK. Suppose I do this. Then you can clearly show that SK dagger SK is MK dagger MK is identity. You can also show that trace MK row MK dagger is same as trace U dagger MK is same as U dagger MK row MK dagger U is same as trace SK row SK dagger. So these two measurements are giving you exactly the same statistics of your classical register. But when you look at the post measurement state, the post measurement state is SK row SK dagger divided by trace SK row SK dagger, which is essentially U dagger MK row MK dagger U divided by trace. Trace is same, doesn't matter.
Yeah. So this is a rotation.
So what is happening is the post measurement state is rotated.
Yeah.
But the statistics is the same. The statistics of the outcome is the same, but there is a rotation on the quantum state. Okay. So some people, to ignore this, what they do, let us look at let us look at SK dagger SK. If I look at SK dagger SK, right? So SK, remember, I've written it here. It is U dagger MK. So SK dagger SK is going to be MK dagger U dagger MK. So which is equal to MK dagger MK. So if I take root SK dagger SK as lambda K, this will be same as root MK dagger MK.
Yeah.
So this is what is our POVM. So we just say lambda, no, I think I need root here. I need root here. I'm going to define this as root lambda K. So then I have summation lambda K is identity. Summation lambda K is identity. And I have lambda K to be greater than equal to 0. This is how a POVM is coming. So a POVM is coming if you kind of ignore this rotation in the quantum state. Okay. That is why they kind of what they do. Okay. Suppose SK dagger equal to SK. Suppose SK dagger equal to SK. Then you observe that lambda K is actually root SK. Sorry, lambda K is actually SK. Sorry, root lambda K is SK.
Yeah.
So then if this was the case, right, if SK dagger equal to SK, then what would be your post-quantum state? If your post-quantum state would be this, right? This, they write it as lambda K rho lambda K. That's all is going on. So take the general measurement when SK dagger equal to SK, and you define SK as root lambda K.
Yeah.
Then you will see that the post measurement state is this root. That is why when you're talking about this gentle measurement, they put the root lambda K at the left and the right.
Yeah. So like while we apply this to some places, like should we see whether the operator being applied is the square root, or like should we just check whether the trace of the original density operator and the POVM applied to it is uh, with high probability?
See, if you look at both the capacity problem and the covering problem, right? We are only looking at positive measurement. So if you see when we designed the decoding POVM for the capacity, we only designed a POVM. So, and we just wanted to show that the post-quantum state is close. So in those circumstances, you only will have with a POVM. You won't worry about the rotation in the quantum state. And hence, that is why the gentle measurement lemma has been written in that form.
Okay.
What if you actually do the measurement with the rotation? All that you can show is that there is some rotation of the quantum state that is not perturbed too much.
Yeah.
Yeah, but keep in mind one thing. If U is a unitary, U rho, U dagger, and rho are very far. They need not be close.
So because it is being rotated.
Yeah, it is rotated. See, U of alpha minus beta U dagger. This is same as alpha minus beta.
Yeah.
The trace norm is invariant to rotation, but you can't just rotate one part.
Yeah.
So really what the POVM in some sense is telling you is that there is some rotation of the quantum state that is close to rho.
Yeah.
And that is enough for all practical purposes.
Yeah, got it. Sir, I have a last question.
Yeah, please.
Sir, in the covering lemma proof you did yesterday.
Yeah.
like you asked us to prove one thing, like
Yeah,
the other terms are small.
yeah,
So
the other terms are small.
yeah, there like while I was doing simplification, I got to a place where I have to show the trace distance is very small by using the gentle measurement.
Okay,
So like it was like trace distance between rho xn and pi xn rho
yeah,
xn pi
yeah,
xn pi.
yeah. Do one thing. You
Yeah,
do, did you have 5 operators on the second term
yeah,
and 1 operator on the left term, right?
yeah.
Yeah, then what you do, you add and subtract again pi rho xn, pi xn rho xn pi xn, you add and subtract and show by parts. So show
Ah,
that
yeah,
rho
yeah.
xn is close to pi xn rho xn pi xn, and pi
Ah,
xn rho xn pi xn is close to pi
oh,
xn rho xn pi xn pi.
yeah. I think you gave this in homework, like so.
Yeah, you don't have any other go.
Yeah,
Y-
now I got it.
yeah, or you can do yeah, see, you can see, okay, I'll write this down. See, you end up with this, right? You end up with this. So you end up with rho. I'm going to be like crisp in the notation. So you'll have pi, pi, pi xn, rho xn, pi xn, pi. Is this what you have? Or do you have
Yeah,
rho
this side
xn here?
also rho xn. Yeah.
Yeah, okay, you have this, right? So do
Yeah.
the following. You consider the following. Pi, rho xn, pi plus pi,
Oh,
sorry,
then
pi
use triangle.
rho xn pi minus pi pi xn rho xn pi xn pi.
Right. Yeah.
Okay. Now this, so what you have done, you have substituted this with rho xn.
Hmm.
So you can show this is small because of pinching.
Yeah.
Here you are doing the measurement pi on closed states, right? I mean,
Yeah.
these two states are closed, this state and this state.
Yeah.
So you can show this term also is small.
Uh, like
I'll tell you. See, pi xn, rho xn, pi xn is close. See, you know this is, you agree with this? You know this is small?
yeah.
If this is small,
Hmm.
yeah, if this is small, do you agree these are close? And trace pi, rho xn, these are close? Do you agree? So do you agree with this? Okay, so do you agree with this?
Hmm. Yeah.
So now,
There should be pi on other side. Right?
no, I'm thinking of this as a proxy for this.
Oh, okay.
Can I?
No, sorry. Pi is a projection, right?
Pi is a projection, yes.
So that's a CPTP map. It will only shrink the L1 norm. I mean, if you apply pi on both sides.
Which you're contesting this thing?
No, I'm not contesting. I'm just saying a way to prove this. Like you have this L1 norm term there.
Yeah,
L1 norm of pi xn, rho xn, pi xn minus rho xn.
yeah,
And the above term is you have just applied pi to both sides.
yeah.
So that is the projection. So L1 will only shrink, right? Pi is a projection.
That's also a good idea. Um, um, I'm not sure.
Sir,
No, in a simple way. I mean, so you want, okay? So hold on. This term is easy, right?
Yeah.
It's only this term that we have to see how to do. Correct?
Yeah.
Okay. Let's see. So pi rho xn pi minus pi xn rho xn pi xn pi. Okay. Um, okay, okay. No, this is cool, man. It's very cool. Okay, it's very cool. See, do you agree this is large? Okay, I got it. So, okay. Do you agree this is large? Hold on. Okay. Okay, you agree this, okay, great. You agree this is large?
yeah,
You agree?
pinching.
Yeah.
Yeah.
You agree, you agree this is, you agree this is small?
Yeah, gentle measurement.
Okay, great. Now, do you agree? Um, so, do you agree this? Okay, so what I'm saying, these two states, call this theta and call this rho xn. Theta and rho xn are close. Correct? So, trace pi theta is close to trace pi rho xn. Do you agree? I mean, this would be maybe some 2 delta or something. Okay, okay. I know you didn't get it. I'll explain once again. See, you agree this is large?
Yeah,
So, well, you actually don't need that. Hold on. Yeah, you need that. So you agree this is large, right? This you agree, right? Statement A. You agree statement A?
yeah,
You agree statement B?
yeah,
Okay. Do you agree with this statement? C says if theta minus alpha is less than epsilon, then trace pi theta is between trace pi alpha plus epsilon and trace pi alpha minus epsilon. Do you agree with this?
That's a gentle measurement.
No, this is measurement between closed states.
How?
Measurement between closed states. So,
yeah,
Srini, comfortable?
yeah.
Sure. Okay, I'll tell
But
you the
the
reference.
expression was like quite
Huh?
different.
No.
Like,
We're coming.
huh.
We're coming. You agree with this?
Yeah,
Now you say theta is pi xn rho xn pi xn and alpha is rho xn. Suppose we know theta and alpha are close. That's what is statement B. So this tells us that I'll tell you. I know it looks crazy, but I'll tell you. Do you agree with this? this.
Yeah.
Okay. Now you apply gentle measurement lemma. What do I have? I have trace pi, pi xn, rho xn, pi xn is very large. 1 minus some 2 epsilon or 3 epsilon or minus some 2 root epsilon, something like this will come. Okay.
Yeah.
Then I apply the gentle measurement lemma. So then I claim this is small. Do you agree? So then I claim. So now I apply gentle measurement. What is gentle measurement lemma, right? Gentle measurement lemma says that if you take a density operator or some state S and you take a measurement pi, if pi S is greater than or equal to 1 minus epsilon, then root pi S root pi is close to S. Correct? You say this is S and this is your pi. What happens? Trace pi, pi xn, rho xn, pi xn, pi minus pi xn, rho xn, pi xn is close.
Yeah.
That's all. See, to show this, I am applying pi on this state. It's exactly what it is, right? To show this is small, you have to apply pi on state S. So when I apply pi on this state, when I apply pi on this state, I want to show it is large. That's what I show here. How do I show this is large? I show this is large by showing that this is close to this.
Mm-hmm.
And that I show by showing this is close to this.
Yeah.
So it's gentle measurement lemma, measurement on closed states, gentle measurement lemma applied in sequence, one after another.
Yeah.
Do one thing. Go to your dinner. If try it out, I can tell you in 5-10 minutes tomorrow. If you don't get it, I'll leave this. I can send this email to you.
Sure.
Yeah, if you want, I mean sit with you 10 minutes and explain tomorrow. It's not a problem.
Sure. Yeah, like I was thinking of like instead of adding and subtracting pi, rho x and pi,
Yeah.
if we add and subtract pi x and rho x and pi x n, would it be simple?
Yeah, I don't think you will get any different. You will go through another route of gentle measurement and measurement.
Yeah,
So you have to
same.
apply this gentle measurement and measurement on closed states one after another. You have to apply 3 times, in my opinion.
Yeah.
So I want to show this is. So I want to show. Maybe I showed a different thing here. Maybe I showed this. I showed this is small. See, the first term is small. I showed the second term is small because I showed that pi applied on this state is small. Okay, you do one thing. Go to your dinner. If you want to come back and you want to talk, you can send me an email. If I'm there, I'll reply.
Sure, sir. Okay.
Yeah.
Yeah, like I'll be back by 9:40 or something.
Yeah. If I don't respond quickly, that means I might not be available. Okay.
Yeah, no problem.
Yeah, we can do it tomorrow. Not a problem. You can just send me an email tomorrow. I can do it.
Okay, sir.
I might have one more short class tomorrow, and so we can do it after class also.
Okay, sir.
Yeah.
I will try and
Yeah. Tell me.
Tomorrow, if you're having a session, I'll also come for it.
Yeah,
if you're doing this.
Sure. I'll let you know.
So just send me an email also. So I'll just come for it.
Sure.
If I'm free.
Yeah,
Okay.
I will do the explanation of this quantum measurement compression slightly differently so that confusion is less.
Yeah. Okay.
Okay. See you then.
Hello. Sorry,
Okay.
I just have one question, if
Yeah.
possible.
Yeah.
Okay. It's about a paper I'm reading. The one line is not clear to me. I'll
Uh,
show it.
let's do it tomorrow. I'm really tired.
Okay, tomorrow after the class, then.
Yeah.
Okay, fine.
Yeah.
Okay, fine.
Okay, bye.
Okay, bye.